All right, here we have day 58. It says a paper towel tube has a diameter of 1.7 inches. So if we draw, it would be a circle, 1.7 for its diameter, and a height of 11 inches. Okay, so it looks something like that. If the tube were cut and unfolded to form a rectangle, what would be the area of the rectangle? So I guess we're just cutting it in one part of it and then down, and then you're going to be unspooling it. So what was the circumference will now be one of the lengths of it. And then the height will remain as the width. So we started with the cylinder and now we have this rectangle. This side is still going to be 11. And then up here, that's not going to be 1.7. It will be the circumference, which is equal to pi times the diameter, pi d, or 2 times pi times the radius. In this case, they gave us the diameter. So we could say it's 1.7 times pi. So this would be 1.7 pi inches. If we want to estimate that value as a decimal, we could type it in a calculator. 1.7 times pi. Gives us 5.3407. So it's about equal to 5.341 inches. What would be the area of the rectangle? Well, the area is just length times width. So we can write 1.7 pi times 11, which would be equal to 18.7 pi. And again, if we want to round that, type it in your calculator. 18.7 pi is about equal to 58.747782. 62. We round that to the nearest hundredth, we'd say that's 58.75 square inches. We know an area will be in square units. The point of this question is that we're basically finding the lateral area of a cylinder. And it's showing that the lateral area is equal to the circumference times the height. You can think of it as like you have that circumference and you're stretching it down by the height. All right, the lateral edges of a regular hexagonal pyramid. So a hexagonal pyramid means it has a hexagon base, so we draw a hexagon down here, 6 sides, and a pyramid means that they will all meet at one point. They say the lateral edges are all 20 centimeters, so those are the lines that I drew in pink. The ones going up the side, they're edges that go from these points on the base up to the top point, the vertex. And the base edges are all 16 centimeters, so those are the ones that I drew purple, so 16, 16, 16, like that. To the nearest cubic centimeter, what is the volume of this pyramid? And then also to the nearest square centimeter, what is the combined area of the base and 6 lateral faces? So that would basically be the surface area. To start with the volume, we know that the volume of any pyramid is going to be the area of the base. So in this case, the area of the hexagon times the height. Now the height is not that 20, the height would be going directly from the vertex down to the middle of the hexagon. I'm going to draw that as h right there. And we can find that height using some right triangles. Redraw that base, so it's more of an overhead view. We have this is 20. And because it's a hexagon, we actually know that all of the sides of the triangles in there are going to be the same because a regular hexagon is made up of 6 equilateral triangles. If you want to prove that, you just go, well, all the angles inside are the same as each other. And we've got 360 divided by 6 slices is 60 degrees. And then the angles down the bottom are the same as each other. So this one is the same as this. Then they must also be 60. So 60, 60, 60. If all the angles are the same, then all the sides are the same for a triangle. So if we know that these base edges are 16, then these lines going from the center of the hexagon to the vertices will also be 16. So that means that this is 16. We can draw a right angle. The height is what we're trying to solve for, and then this hypotenuse here is 20. So if we set up the Pythagorean theorem, we could do 16 squared plus our height squared is equal to the hypotenuse 20 squared, which our hypotenuse is the lateral edge. Now we know that 16 is 256. H squared is what we're going to be solving for, and 20 squared is 400. We could subtract 256 from both sides, giving us that the height squared is equal to 144. So we just can do the square root of both sides because with the geometry problem, you don't have to worry about a negative solution. In this case, that would mean that our height is equal to 12. Square root of h squared is h, square root of 144 is 12. We still need to find the area of this base. So the area of the hexagon, you can do that by finding the area of one of the triangles inside of the hexagon and then multiplying it by 6, because for a regular hexagon, all of those triangles are congruent. For an equilateral triangle, when you drop an altitude, you will actually cut it into 2 30, 60, 90 triangles, right? There's 60 cuts it into 30 and 30. These angles stay down at 60. So if we know that the entire side is 16, then half of that, when it's cut in half by the altitude, will be 8. We got 8. Our hypotenuse will be double that, that's 16. And the ratio of sides of a 30, 60, 90 are x root 3, 2x. So we have the x and the 2x. Our height is the side opposite the 60 is x root 3. In this case, that'd be 8 times the square root of 3. So the height of each equilateral triangle is 8 root 3. If you want to find the area of one of those triangles, we would do base times height over 2. The entire base is 16 times our height is 8 root 3. Then we have to divide by 2. 16 divided by 2 is 8, so 8 times 8 is 64. 64 root 3 will be our area for one of those equilateral triangles. Now, if we want to do the entire hexagon, we know that the area of a hexagon is equal to 6 times the area of one of those equilateral triangles. 6 times 64 will give us 384, and then we still have that square root of 3. You could type in 384 times the square root of 3 in your calculator and get an estimate, but because that's not our final answer, I'm just going to leave it in that form, in simplest radical form, and plug it in like that until I get to the final answer. Now, I actually misspoke before. I said the volume is equal to the area of the base times the height. That would be for a prism. We actually want to find a pyramid, and a pyramid will be 1/3 of the equivalent prism. So instead of area of the hexagon times height, we're going to do 1/3 of the area of the hexagon times the height. And the volume will then be equal to 1/3 times the area of the hexagon we have right here is 384 times the square root of 3. Units were centimeters squared for that. It's an area. And we're going to be multiplying that by the height. We have the height right here would be 12 centimeters. So if we multiply that out, we'd get 1/3 times 12 is 4. 4 times 384 is equal to 1536 root 3. Right, so that would be in simplest radical form. Volume would be cubed. If you want to get an estimate for it, round it to the nearest hundredth. 1536 times the square root of 3, which is about equal to 2660.43 cubic centimeters. They said to round to the nearest cubic centimeter, so 43 is closer to 0 than it is to 100. We would just say 2660 cubic centimeters is our best approximation there. Now, they also are asking for the surface area. So it's to the nearest square centimeter, what is the combined area of the base and the 6 lateral faces? That makes up all of the surfaces of the shape. Well, we already have the area of the hexagon. If we write this out, our surface area is equal to the area of the hexagon plus the 6 triangles, the area of the 6 triangles that connect the vertex point, the apex point, to all of those vertices down on the base. So we already have the area of the hexagon right here. We could just plug that in. But what we need to find is the area of one of these triangles. It's not the same as the triangles that make up the hexagon. These triangles, move this so I have a little more space. We've got 20 for this side, 20 for this side, and down here would be 16. We could use trig, right? We could drop down an altitude like this, and then break that into 8, find the height that way. That would be the slant height of the actual figure. Or we can actually use the Pythagorean theorem, because we know we have 16, it's going to be cut in half by that slant height. So that's going to be 8. So we have 8, our slant height will be there. I'm going to label that as L. And then 20 is our lateral edge, the hypotenuse of this right triangle. So if I were to write this out, we could say 8 squared plus our slant height squared is equal to 20 squared. 8 squared is 64. L squared is, again, what we're solving for. We're solving for L, equal to 400. So we can subtract 64 from both sides, leaving us with L squared is equal to 336. 336 is not a perfect square, but it does have 16 in it, right? It's a multiple of 16. So we can do 336 divided by 16, which gives us 21. So the square root of 16 is 4. If we do the square root of both sides, you'd get the square root of 16 times the square root of 21. We could write that as 4 times the square root of 21. So our slant height is 4 root 21 centimeters. Now, if we want to find the area of this triangle, again, I'm going to shrink some of this work that we already have done. We could say the area of the triangle is equal to 1/2 times the base, which our base is 16, times the slant height. The slant height is the height of each of those little triangles. We just said that was 4 root 21. So we'd say the area of the triangle is equal to 1/2 times 16 is 8. Our slant height, we said, is 4 root 21. So 8 times 4 gives us 32. Our area of the triangle is 32 times the square root of 21 centimeters squared. Plug this in for our area of the triangle, and then we'll solve our surface area. Our surface area is equal to 384 root 3 centimeters squared plus 6 times 32 root 21. I'm not even going to solve it in simplest radical form because it would be a little bit ugly, but we've got 384 root 3 plus 6 times 32 times the square root of 21, which is about equal to 1,544.962044. Making some space, we're rounding that to the nearest square centimeter. So we could say the surface area is about equal to 1,545, right? 96 rounds up, centimeters squared. That would be our rounded surface area and our rounded volume. All right, next we have the surface area of a sphere. The surface area of a sphere is found using the formula 4 pi r squared. So the surface area equals 4 pi r squared for any sphere. Find the surface area of the Earth, given that its diameter is 12,742 kilometers. The main trick here is that our formula uses radius. They gave us the diameter, so just make sure that you find the radius, knowing that our radius is equal to half of the diameter. So in this case, our radius is equal to 12,742 divided by 2, which would be 6,371 kilometers. We just plug it into our formula. We'd say surface area equals 4 times pi times the radius squared. In this case, that's 4 times pi times 6,371 squared. That's 162,358,564 pi kilometers squared. If you want an actual estimate in terms of kilometers squared, you just multiply that out. So type in 162,358,564 times pi. And now it's giving me surface area is 510,064,471.9 square kilometers. That's rounded, right? So it's about equal to that. And it's rounding anyway, I would just put it in scientific notation. So for scientific notation, we'll put one digit before the decimal place. So in this case, we'll do 5.1. You could go 5.1006444719. I'm just going to round it to the nearest hundredth. So 5.10 times 10 to a power. In this case, you're making it bigger than 5.1. So how many times would you have to move over the decimal place? Well, it's 1, 2, 3, 4, 5, 6, 7, 8. 8 places, so it would be 5.10 times 10 to the 8th square kilometers is our estimate for the surface area of the Earth. Now, this is assuming that the Earth is a perfect sphere, which it's technically not, but for the purpose of this problem, this would be our good estimate. Next, we have the volume of a pyramid is 1/3 times the base area times the height. Right? That was the formula we used above that technically I actually wrote incorrectly at first. Make sure you have that 1/3 if it's a pyramid. This formula works for cones as well. So in that case, the base area would just be the area of a circle. So your base is a circle, so that'd be pi r squared. Find the volume of a cone with a slant height of 13 inches and a diameter of 10 inches. So if we were to draw a cone, circle up top, diameter is 10, and your slant height is 13. We need to find the actual height, right? We know the volume is equal to the area of the base, so it's going to be pi times the radius squared times our height. Now, what we can do is make a right triangle here where the height is one of the legs. The other leg will be the radius, so we have to do half of the diameter. Half of 10 is 5. Now we could do the Pythagorean theorem. You could do 5 squared plus height squared is equal to 13 squared. Or if you know your Pythagorean triples, 5, 12, 13 is one of those that will work. But just to prove that it does work, we can do 5 squared is 25, 13 squared is 169. If you subtract 25 from both sides, it gives us that the height squared is equal to 144. Square root of both sides gives us that the height is equal to 12. Units for inches, so it's 12 inches. As we said, the radius is equal to 5, just half of the diameter. So if we plug that into our formula, we get that the volume is equal to pi times 5 inches squared times our height of 12. It would be 25 pi times 12. 25 times 12 gives us 300, so our volume is equal to 300 pi cubic inches. And if you want an estimate of that, you would just type that in, 300 times pi, about equal to 942.4777961 inches cubed. And find the volume of a cone. They don't say what to round to, so let's just round to the nearest hundredth. Our volume is about equal to 942.48 cubic inches. Now you'll note that I always write about equal to even if I'm going really far back, because this is still an estimate. Right? This number is a multiple of pi, so it's going to be an irrational number. It goes on forever. The only way that you get an exact answer is if you leave it in terms of pi. You can leave it in terms of pi or round to an appropriate decimal place. All right, next we have the radius of the sun is 109 times the radius of the Earth. Find the surface area of the sun. Well, there are two ways we could do this. So method one is to scale the radius. I would say the radius of the sun is equal to the radius of the Earth times 109, right, times the scale factor. Or our second method is to scale the actual surface area. Right, since we already found the surface area of the Earth in the previous problem, we could just scale that appropriately. In that case, we know that when you scale up an area, you have to scale it in 2 dimensions. So you're actually multiplying by the scale factor twice, or the scale factor squared. So we would say the surface area of the sun is equal to the surface area of the earth times k squared. In this case, our k is 109, so times 109 squared. Because we already have the surface area of the earth, this method would be faster, but I'll just show that both methods will get you to the same answer. First, if we want to find the radius of the sun, we'd say it's equal to the radius of the earth, which in our previous question we found to be 6,371 kilometers, times 109, times our scale factor. 6371 times 109 gives us that the radius of the sun, 694,439 kilometers. Now, if we were to plug that directly into the surface area of a sphere formula, we'd say the surface area is equal to 4 times pi times the radius of the sun squared, which would be 4 times pi times 194,439 kilometers squared. Right, so if you square that number and then multiply it by 4, we get that is equal to 1.928982099. It says E12 on your calculator. E just means times 10 to the power of, so it's times 10 to the 12th pi. Let's just multiply that by pi. Since we're already rounding, we might as well round it in terms of pi. And this gives us 6.060075991. Again, this is E12, so that's times 10 to the 12th power. Our units are kilometers squared. All right, so if we round that to maybe the hundredths place, it would be 6.06 times 10 to the 12th square kilometers for the surface area of the sun. All right, so that's one way that you could do it. Again, since we already found the surface area of the earth, we could also do this other approach, which will be a bit faster. Say our surface area of the earth, let's do the less rounded answer. So that's our surface area of the earth, and we're going to multiply that by 109 squared. And that gives me that the surface area of the sun is about equal to 6.060075991 E12, so that's times 10 to the 12th power. Again, this would be kilometers squared. So you can see that, this is actually the same number we had down here. Just got to it fewer steps. If we round it the same to the hundredth place of this scientific notation, that'd be 6.06 times 10 to the 12th square kilometers. And this proves that this works. You can scale up just the length of the radius by a factor of 109, or we could scale up our surface area by 109 squared. You get to the same answer. Now, I would recommend, if you already found the surface area of the first thing, then this method is faster. If you have time, it's worth doing it both ways so that you can prove to yourself that your method does work. All right, so that's how you do all the problems from day 58. If you have a better approach or faster approach or just a different approach to any of them, or if you have any questions, feel free to comment below. Again, make sure for the volume of a prism, do not do what I said the first time. It's going to be volume equals 1/3 times the area of the base times the height. If you have a prism, that's when you do the area of the base times the height without the 1/3.